Hi, welcome to our fifth webinar. I'm June Adams, the CEO of Powercalc, and today we're going to start off with a quick demonstration of Powercalc, including our just launched automatic graphic and simultaneously generated one-line diagram. Then we're going to do a deep dive on AIC ratings. Next week, we'll have our grand finale, and we're going to do an overview of Powercalc, again, our one-line diagram, as well as review our sessions on voltage drop, AIC ratings, and fault current calculations. Today's demonstration will be on a mid-rise residential project, and we ask that you hold your questions until the end of the demonstration. And now I'm turning the webinar over to James. Thank you.
Hello, everybody. This is James Khalil. I guess it's good morning to people that are on the West Coast, and good afternoon to the people that are on the East Coast. This is our fifth webinar session for this year so far, and we'd like to start right away, I guess, that everybody is online with us. Okay, so let's go ahead, like June said, dive into it. Hopefully everybody can see my screen right now. We're gonna go to the same project that we worked on for the last four sessions, I guess, which is a mid-rise building named Middle River here in Fort Lauderdale. We preset the panels and power distribution system. So to start the project, you go to the project information and put the project name. And after you do that, you go into the control panel to input your panels. If this is a start from scratch, all these panels in here that you see right now in dark gray and blue and red would be blank, and then you go ahead and build it up one by one. The concept in Powercalc is to start from the bottom up. That's from the light switch all the way to the panel. And then from the panel, you go ahead and build up another panel, and then all these panels can be connected to a distribution panel or to the main distribution panel, depending on your project. So let's just kind of summarize a little bit to get us from the start all the way to the AIC. Usually the AIC calculations and the fault current calculations traditionally happens at the end of the project. After you design everything and you input all your circuits and all the mechanical equipment and so forth, as shown here at the bottom with the red buttons, and then you go ahead and start your calculations. That's not happening with Powercalc. Powercalc will do the calculations as you are building up your one-line, your power distribution system, all the way to from the panels all the way to the distribution MDP or DP panel. So let's open a panel to one of the units. All right. Again, this is the same panel that we used in the other webinars, in the previous webinars. You start filling up the panel or setting up the panel. So this panel here, named 201, which reflects unit number 201 in the mid-rise building. And then you go into the control panel. And let me move this out of the way. Start with the wizard of the panel module to set up the panel. And all we need to set up here is determine the voltage and the phase for this particular panel. And the way you do that, you go into the panel board characteristics and you go across and you see the line voltage. It's right now is set on 208. If it's different, you can go ahead and set it up with traditional voltages that we have here in the United States. So I'm going to just, for the sake of demonstration, change this to a 203, to 230. So, and then leave all the other fields that are set on auto, keep them on auto. That way that any modification as you input the circuit into that panel, all these variables will update itself automatically and display the correct value that is needed to support all the loads that you're going to input there. So we changed this from 208 to 230. And then the other one that you need to be aware of is the number of spaces. So you go to the panel board features and you can change the spaces in here to fit the job. You can go all the way from 6 spaces all the way to 84. I'm going to change this from the 42 to say 56. And then close and calculate. All right, so now it calculated. If you go to the top of the panel here, the header, you see that the voltage changed from 208 to 230 and is set on single phase. Of course, at the start of the project, you're not going to have any of this information in the center of the panel board. But again, for the sake of the demo, we've pre-filled up all these information for you. But so to set up the panel, I went to the wizard for the panel board wizard. And then now we're going to go and fill up the panel circuit by circuit. So let's go ahead and choose one of the circuits that we just added. So it'll be the circuit 43. So now to input a circuit, there's 2 ways to input a circuit, either to be directly on the panel schedule, or the other way, it will be through the wizard. And to set up a circuit, all we need is to input is 3 values. It would be the load KVA, the load, the number of poles for the load, and you can select that from the pull down menu. And then you also can select, you have to input the load type, and there is a load down, pull down menu for that also. You need to select one of those load types. For this particular one that we input already, that's a kitchen receptacle, or the that is required to have 2 separate small appliances circuits in a residential rated at 1.5. So we'll put 1.5 in here. And then we selected the number of poles to be 1, and then we selected the load type, and that's the load type would be receptacle. So we change it to a receptacle, and then you go ahead and calculate. All right, now, so that's one method. The other method to input the circuit is to go through the control panel of this panel 201, and then on the right side of the control panel, you see the wizard branch circuit inputs. Click on that. And then you can go ahead and input circuit by circuit. So this here right now is displaying panel 201, circuit 1, which again, it was pre-filled. And we changed just the load type to an R, so it's displaying to you the R. Down here is the branch circuit characteristics or values. And down here, the fourth, or the 1, 2, 3, 4 row is adjustment. If there is needed adjustment to fit that particular design, you can come back in here and do these adjustments. So let's input circuit 43. So you can select from here. Doesn't want to scroll down. Okay, let's go ahead and select 42. It's right now is a space. So let's go and change that to a, let's say, dining room or a bedroom circuit. So let's say it's a, let me make it cap. Bedroom. Caps off, caps on, okay. And input the load KVA. It's 1. Number of poles is to be selected from the pull down menu. So it's a single pole. Load type selected to be R for receptacles. And that's all what we need for this in order for the circuit to calculate the values. So now we're going to go ahead and close and calculate. So if we go to circuit 42 on the right side of the panel, here it is with my misspelled bedroom, or kind of spelled funny. So here's the load, 1 kVA. The number of poles is 1, and the load type is R. You see that the system or the software calculated for you the circuit values in here. So this is a 2, number 12 conductor with a number 12 ground, 1/2 inch conduit, and for a 3% voltage drop, you can actually travel 344 feet with this particular circuit. And in the previous sessions that we had about the voltage drop, we showed you how to adjust that. If the circuit is longer or shorter, how you can adjust that. And again, the system will adjust all the related values automatically for you by just adjusting the circuit length, or adjusting the conductor size. It will adjust the circuit length for you. Okay. We probably, if we have the time, I will show you that in details later on. Or you can go back, I think it was session number 3 that we talked about the voltage drop. Now, if the addition of that circuit also affected the size of the feeder of the particular panel, the feeder will be adjusted automatically for you and be displayed, and it will carry all that through the power distribution system. It will, if that panel, which I think it's fed from MVP, if we look in here, it's MDP circuit number 2. It will take that load all the way to MDP, adjust MDP, adjust everything related to MDP, and adjust the service and all the related calculations. So we input the circuit, calculated the load, and it tabulated all the load types for you, by load type for you down here in the calculation block. You can see that by load type R, it did the demand value for you. The first 10 kW at 100%, so the demand load is 10, and then the remaining at 50%, it'd be 14.5. But since this is a residential, you have actually an additional demand, or be actually less demand on the receptacle load. The code ask you to make it at 40% rather than in a commercial building at a 50%. So you put the 40% in here, and it will calculate for you the demand load. And then we'll add all the demand loads and figure out the amperage associated with that particular load. Now, this is a new project or a new facility, a new home. So it's the first 10 kW will be demanded at 100%. If it's a remodeling job or project, the code allow you to, will give you a break, I guess, if you will, and it says if you can actually demand the first 8 kW at 100%, and here's what you change it. You change it into an 8 and calculate. So it took that load, connected load, and demanded at 40%. I mean, the first 10 kW at 100%, and then the remaining at 40%. And we'll go ahead and adjust all the other values, if you will. It will adjust this if it need to be adjusted. The other, I guess, feature that we have on the panel board itself, this panel here is rated for 230 single phase. Say for whatever reason you decided to go into a 208 3-phase instead of a single phase. Well, you don't have to go ahead and recircuit the project. You don't have to go ahead and reconfigure all the circuits for you. All you have to do is to go back to the control panel, go to the panel module wizard, go to the voltage, and change it to 208. And go to the phase and change it to 3-phase. And close and calculate. Okay, so it changed up here, it changed the voltage to 208, 120 on the line to neutral, to 3-phase, and went ahead and adjusted the conductor size. I don't know if you remember, before we made the change on the voltage, it was 4 odd, and now it's 350 to support that load. And if you look here, it activated phase B and just shoveled the circuits around, but did not change the circuit number. So you don't have to go back to the floor plan and change the home runs. It just really readjusted them and kept everything in perspective to the original design. So if that circuit number 3 was originally on phase C when we had the single phase, it just moved it down to shift that load to phase B, but it didn't change the circuit number on you. So your home run on the plan stayed the same, and we didn't have to make any modification. Now, in the background, as we're doing all these changes and adding panels, deleting panel, moving panels, changing the voltage drop, adjusting the conductor sizes, all of this is happening, and there's other things happening in the background in terms of figuring out the one-line diagram, the layout of your power distribution system, and then the fault calculation, the voltage drop calculations, the AIC rating changes. You don't have to go ahead after you do your design and you made all the changes that's required, and then you go and do your calculations after the design is done, to go ahead and finish your fault current calculation. No, it's happening at the same time. So any changes from now until the project goes out of the door to the client, again, you can come back to this particular panel. If there's a change in that panel, you can go ahead and make that change, and it will adjust everything for you. Okay, so the topic for today was supposed to be the short circuit calculations and the AIC ratings. Just a brief description of what's the short circuit, what's the AIC. Now, I'm going to assume, of course, that I'm not going to go into the theory of all these values and how we accomplish these values. That would be left for the, I guess, part 2 of all these sessions. Is we're going to go back and talk about the engineering values or the engineering calculations and the engineering equations that are used for all these values, whether it's the branch circuit or the feeder, the conduit, and then the short circuit calculations, that sort of things. Right now, we're just demonstrating to you how Powercalc is doing all these calculations for you to make it easy on you and give you a much better quality product, so there's no error and mistakes done. The AIC stands for amperage or ampere interrupting capacity. It's the maximum fault current that an overcurrent protection device will safely clear when a fault is applied at the load side of the overcurrent protection device. The key word here is the overcurrent protection. It's a rating for the actual overcurrent protection device. It's the circuit breaker or the fuse that's inside that panel or inside the disconnect or any of the equipment. Now, short circuit current rating, SCCR, is a rating on a component or an assembly representing the maximum level of short circuit current that said component or assembly can withstand without sustaining any substantial damage. So AIC is the rating of the device, overcurrent protection device, the circuit breaker or a fuse. The short circuit current rating is related to the component, to the panel itself, and not the devices that's inside that panel. And these are 2 different ratings that are required by the NAC to be listed on these particular components and devices. So now that we define what's AIC and what is the short circuit current rating, let's move forward and show you how the Powercalc does that calculation. Again, it's as easy as 1, 2, 3. As we input the circuit parameter that we need is the KVA, the number of poles, and the max load type, and then the system will go ahead and perform all the calculations necessary and display the values respectively, whether it's going to be a branch circuit or the feeder size or the panel frame or main rating and so forth. Now, so let's go and execute the AIC or the short circuit calculations. Click on the control panel, and then you see a series of buttons on the left side. One of them says short circuit calculations. So click on that. In the upper portion of that sheet, the short circuit calculation worksheet, you see short circuit calculation ribbon with certain values that you need to input. And then below that, there is a table. Let me zoom out a little bit. It's too much, I think. All right. You see, it's actually a list of your power distribution system. It starts with the enclosures. These are all the panels that are listed in your distribution system. If I go to the control panel here, that's these panels in the blue, okay? They're all listed in the short circuit calculation form. And then underneath it will be the distribution panel, so distribution panel S, and then underneath it will be the MDP. These, and then throughout the chart, it will show you the pertinent information that is needed for the short circuit calculations, and then thus it will go ahead and calculate from the short circuit calculation value, it will go ahead and calculate the AIC rating associated with these particular panel boards and distribution panels, okay? By the way, just also, if you scroll down, this is also a list of all your equipment that is in the system or in your power distribution system. So this is here, again, is the graphic mapping, if you will, of your power distribution system and showing you the summarized values for the feeders and the overcurrent protection device sizes and so forth. So we start talking about the top section of it. If you go to a little bit to the right on the method, there are two methods, whether it's going to be manual or automatic. If you put it in automatic, it will ask you for a value of the transformer, and then from that value of the transformer and the associated voltage, it will calculate the maximum lead through of that particular transformer, and then give you the short circuit rating at the MDP. So if you don't have the information from the utility company about the fault available at the service point, and you want to estimate it yourself, you can do that. But if you have the actual value from them, you can input that value manually. So we go ahead and set it up on manual, which most of the time, like 90% or even maybe 95% of the time, you set it up on manual because the power company or the utility company in your jurisdiction or in your area will give you the available fault, and it's actually the preferred method. Instead of estimating what it could be, you actually get an actual value, that true value. So if it's on manual, you input the that value, the transformer led through or the short circuit value in here, and that's the value that the system or the Powercalc is going to take as the starting point for the remaining of the calculations. So by inputting this value in here, if we go down to the MDP, it goes to the MDP and says down here that the parent is 18,000. That's the value of the lead through of the transformer, and then it takes into consideration the feeder size and the feeder length from the transformer to MDP, and then calculate what we refer to it as the child. So the parent was the transformer and the child was the MDP. So that value of 18,000, by traveling all the way from the service to the from the transformer to the panel MDP, it was reduced to 7728. Again, let me just enlarge it a little bit so you can see it. If the internet wants to cooperate today. Anyway, it's 7728. And then it went ahead in here and recommended the AIC rating of the child panel, which is the MDP. Now, all subsequent upstream from MDP will take that value, which that's the amount of fault current available at that point, at that panel, and then it's going to travel to upstream to the panels and the disconnects and the building equipment and so forth. So it's going to take that value and as the starting point for the calculation to the next panel, to the next building equipment or disconnect. Regardless of that, the panel itself is rated for 10,000 AIC rating, 10,000 amps. So if we go back to here, you show, like we show on the second panel, that at the parent panel, it's 7675. It's supposed to be very close to the 7728. It depends on the conductor size and whether it's running a conduit underground, not underground, all that stuff. So, but it's very close to as the child, and then it will go ahead, consider that now is the parent. The 7675 is the parent panel, and now the child, which is this particular panel, second one, is now the available fault is 6675. It will go ahead and select the AIC. Now, you can see that the AIC values are kind of in a frame sizes. The manufacturers, I guess, from the experience and from various calculations, decided to build their overcurrent protection devices based on certain frames, if you will. So it starts from 5,000 and then it goes to 10, I think 18, 20, 22, 24. And there is a pull down of these values. I'll show it to you in a little bit. So the software go based on the fault current available at that particular device or component, the panel, and go and select an AIC rating that is equal or higher than the available fault current. Same thing on the next panel, same thing on the next panel, and so forth. Now, if any of the related parameters have changed, meaning if the input transformer value have changed from FPL, or the MDP feeder have changed, or you increase the load on panel 201 or panel 202, all these values is going to go ahead automatically adjust for you, and then adjust the AIC ratings automatically and display it on the panel. So where does these information get displayed on the actual panel? So if we go to panel, say again, since we're working on panel 201, here's panel 201. In the panel code characteristics, you're going to find there is, I guess, the mount. It's noted, meaning on your plan somewhere would be noted. There's other selections that you can select by going into the panel wizard, and you set it up that way. And then it says the AIC rating, capacity. It says rating fully rated. There are two type of method to calculate the AIC rating. One of them is the fully rated, and the other one is series rated. And then it displays for you here the rating of the AIC for that particular panel should not be less than 10,000. Now, again, you can preset that, or you can go ahead and set it up manually if you're not in agreement with the calculations that you want to give more capacity, just maybe in the future that changes in the overall power grid. You want to give the client a little bit more capacity. You can go back to the control panel, go to the wizard, go to the panel board characteristics. Here is the mounting is noted. You can go ahead and change that, say surface, recessed, or whatever you want it to be, change it. And then here's the fully rated or series rated. And then the AIC is set up on auto, so it picked up the value that was calculated at the short circuit calculations. If you're not in agreement with it, you can go ahead and say, well, I want to give them 14. And these are the industry standard AIC rating that is widely used throughout all the manufacturers. You might find some differences. Instead of a 24, sort of 25, some would be rated for 24, but again, it doesn't make that much difference when it comes to the different frames and so forth. Now, so if you're in disagreement with the number, with the 10 kA, you can change it to 14. So I'm going to go ahead and change it to 14, and everything else has stayed the same. So close and calculate. We'll go back to the panel and we'll see what took place calculation-wise. It went ahead and calculated and changed it to a 14 and changed it to a red background to indicate to you, the user, that the auto value have been overridden with the 14 value. Okay, so you can go ahead and change it. Now, when you change it here also, if you go to the control panel and go back to the short circuit calculation, it should indicate that it got changed from the 10 to the 14, and here it is. They changed it from the 10 to the 14. But it kept the same fault current because there was nothing have changed in the characteristic or the values that drive the short circuit calculation, which there's primarily 2 or 3 elements or factors that affect the short circuit calculation. It's the voltage of the system. Second one is the impedance and the length of that impedance. These are, which is basically Ohm's law, that R equals V times I. I'm sorry, I equals based on Ohm's law, R equals the voltage divided by the amp. So the values that affect the amp is going to be the R, the impedance, and the voltage. Of course, related with the impedance will be the distance that that particular fault, that particular current is going to travel. The longer the conductor size or that particular conductor, the longer it is, the more energy is going to be dissipated through that conductor, and thus the fault current at the end of the conductor, it would be less the longer it is. Okay. And again, in the part 2 of all these seminars, we will talk about all these theories and what affects all these values. So it will give an idea to the designer if he is not in agreement with some of these values or the output, what can he do to adjust these values or to improve it, just in case that, hey, the AIC all of a sudden is 65 or 100,000 amps, and you would like to reduce it. What can you do to reduce that value to make it more economically, I guess, feasible to be supported by the project? Okay, so let's go back to the panel by clicking on it in here. Of course, the other way to do it is to go to the control panel and click on that respective panel. So we talked about the AIC now. So now that panel is rated for 14,000. So what's the relationship now between this and the short circuit current rating, the SCCR? The SCCR has also to be listed on that particular panel to be able to support that device AIC rating. Now, so if the entire system was rated for 10, based on the original calculation, and you decided to change this particular panel to a 14, now really that panel is not going to be protected because the entire system is about 10,000, or the panel itself was 10,000, and you decided to change the circuit breaker, the main circuit breaker, or the breakers here, the branch circuits, to the 14. So you really did not gain anything unless you change the entire system. So hopefully that clarified the differences between the AIC and the short circuit rating of the equipment. I think that discussed everything, or we talked about everything that is related to the AIC and the entropic ratings. We also talked a little bit about the load type. One other thing, actually, which a couple of questions that came from our clients, is what is the difference between the panel and the distribution panel? there's a little bit of a confusion here. When we design Powercalc, we tried to mimic the image of a lighting panel and then a distribution panel. The lighting panel, traditionally, we have been listing by circuit number per pole. So if you have a 3-pole circuit, it will actually occupy 3 rows on the panel. The distribution panel is different. If it's a 3 or 1 or 2-pole circuit, it will only occupy 1 row. And I'll show you what I mean by that. So this panel here say that the first circuit is actually a 3-pole circuit. I'm going to go ahead and change it to a 3-pole. It would take that load, 1.5 load, total load, and divide it on by 3 and list 1/3, 1/3, 1/3 on each of the phases. But each phase or each pole is in a separate row. So when I change that load from a single pole to a 3-pole, it took the 1.5 that I put in here on the circuit number 1 and divided by 3 and put the values on circuit number 1, 3, and 5. And also divided that load between the 3 phases, 1/2 and 1/2 and 1/2 here. There's a 0.8 from the other side of the panel. So it was added up to here. If I take that out, it will be 0.5 and listed as 1 circuit. So now you cannot input anything in here at all. You cannot select or input anything. This is reserved by the 3-pole circuit. Let's go to a distribution panel. A distribution panel, when each row can be a single pole or a 2-pole or a 3-pole circuit. Okay, so this particular panel, this distribution panel, is a 3-phase. So if I go ahead and put 16 kW in here, and it's for 2 poles, actually, let me go ahead to an unused circuit. So let's say I'll go ahead and put 15. So it would be easy for us to divide it by 3 and select 3 poles and select the load type. Let's say it's a heating type and calculate. So it took that 15 kW and divided by 3 and spread it throughout the 3 phases, 5, 5, and 5, A, B, and C, but they're all in the same row. If I change it to a single pole and calculate, it took the entire circuit or the entire load and put it on phase A and adjusted the feeder size and the conduit and everything for you, and updated all the values that affected by that particular change or addition of a load. So that's really the main difference between a panel and a distribution panel. It's the load, when you input the load on a panel, and if it's a single phase, it would take 1 row. If it's a 2 poles, it would take 2 rows. If it's a 3, it would take 3 rows. On the distribution panel, a 1 or a 2 or a 3 pole circuit will only take 1 row. Okay. Other than that, again, the system will go in and calculate the same way, and everything would be updated accordingly. If you want to change it to a 2-pole or a 3-pole, it will go ahead and change that for you, and you don't have to worry about anything. Another question was about the abbreviation button in here. See what happens when I click on it and activate the abbreviation. It will actually list all the abbreviation that is used into the system. If I click on it, activates it, and here's the abbreviation that are used throughout the system, which again, these are industry standard abbreviation, which most likely, I would say 99% of it matches your abbreviation that you are using if you're using ANSI and industry standard type abbreviation throughout. With that, I think I'm done, and I'm gonna go ahead and leave that open for questions. So make sure that thank you for joining us today, and that I want you to remember to really sign up for your free 30 days trial. You'll be happy with the product. It will really give you a higher quality design with a much less design time, 40, maybe even to 60% less design time, but much higher quality. The thing that we did not display for you today was the one-line diagram. So, and again, as I said in the starting, that all this is happening in the background. So all these changes that we have done, all the moving of circuits or moving a panel from this point to that point has been updated automatically, and it will display the one-line diagram for you with all the appropriate values. If we decided again to change something, it will give it, it will make that change for you. It's happening in the background. It will also, the panel boards are all filled up, and you can import them into AutoCAD as well as with the one-line diagram. Thank you very much, and I open the floor for the questions.
Hey, James. I got a question. Can you give us an example of how the SCCR and the AIC are related?
I think the question, if I understood it, is how the AIC, the amperage tropic capacity, and the SCCR, the short circuit current rating, are related. The common point between the two the two ratings is the fault current. Okay, so you perform your fault current calculations first, and then based on that value, now the short circuit calculation, as we talked about it last time, is this is the worst condition that the system will ever experience during a malfunction of a circuit breaker or an accidental contact between the two conductors. So if anything catastrophic happened, it will be related to, that's the maximum short circuit current that will pass through the system. So the equipment has to be rated to sustain that amount of energy and react and open and clear that fault without any catastrophic damage to these pieces of equipment. So as an example, if the panel board has a 65 kA SCCR, and the panel, the breakers having also the same AIC rating of 65, we call this is a fully rated short circuit current rating between the two different components, the breaker and the panel itself. And that system now can sustain up to 65,000 amps of fault current. So say that we calculated the fault current and it was 52,000. So the nearest standard frame, if you will, industry for the short circuit rating and the AIC would be the 65. Now, meanwhile, if your breaker was rated for, say, the 22 or the 25, but your panel is rated for 65, so now the entire system is not rated for 65 anymore. It's rated for the lowest value of the two, which is would be the 25,000 amps. Again, that's based on the fully rated. So the manufacturers will stamp, or supposed to stamp, what is the short circuit rating of that particular panel that's going to house these circuit breakers. So if circuit breakers are lower than that short circuit rating, that panel now went down from the 65 to the 24 or the 25,000 amps. Now, if your circuit breaker is rated for 100,000, which is higher than the short circuit rating of the panel, now that circuit breaker, you have paid too much money for it, and it's useless because now still the system the entire system will be rated for only 65,000, and you cannot have a short circuit current higher than that. So that's why it's very important that you have the equipment, the panel rating, short circuit rating, stamped on the panel, so you know what is the maximum value of the circuit breaker amperature tropic capacity can be inside that panel. Otherwise, you have paid too much money either for the panel or for the circuit breaker, depending on the ratio or the rating between the two. Hopefully that answered the question. So basically they go hand in hand, and they're both based on the short circuit calculation. Okay?
Yeah, great. Thank you, James. One more thing. How do you know if the design was based on fully weighted or series-related methods?
Oh, I talked about that. I guess that I didn't talk in details about it, which probably we'll talk in details about it when we go into the actual theory behind those. Okay, fully rated means the component and the circuit breaker are stand-alone. That if I have a circuit breaker that's stamped 10,000 amp on it, that means it can sustain up to 10,000 amp to go through it without any physical or destruction or starting a fire. So it would be intact for that particular value of fault going through it. Same thing for the short circuit rating of the panel. It's rated based on a fully rated. Now, the series rated is that the theory behind it that I can have two devices in series, a circuit breaker with a circuit breaker or fuse with a circuit breaker, that the value for the short circuit calculation, short circuit values available at that point can be actually higher than the AIC rating of a panel if it is actually protected by another device upstream that has a higher AIC rating. The theory behind that fault, when it passes through the higher device AIC rating, say the 10,000, it's only going to pass through to the next device downstream from it a low amount of energy or current. So the lower AIC rating circuit breaker will take that hit without being damaged. I am not an advocate of the series rating because it's always related to these specific two pieces of overcurrent protection device that we're making the assumption that the one upstream is going to protect the one downstream. But what happens if you actually change that circuit breaker and you didn't know the relationship between them, and you changed it, and then the next fault is actually is larger than what the circuit breaker downstream can sustain, and you will be having a fire or damage to the equipment. So basically, fully rated means it stands alone by itself. It can protect you during a fault incident by itself. It has the enough capacity in it to, or that design-wise, to sustain that fault. Series rated, it relies on two pieces of equipment, one with a higher AIC rating, and then the one, the downstream would be with a lower AIC rating, under the assumption that the test from the UL has tested these two pieces of equipment or devices in series and found that the one downstream will protect, is protected by the one upstream. But I don't like it because, again, if the maintenance guy or the electrician have changed one of the two, that relationship is broken unless you actually replace it with the exact brand name, the exact size, the exact frame. Everything has to match exactly the original installation of the original design. Otherwise, you will be causing a problem. Okay? Any other question?
Thanks, James.
You're welcome. Okay, so I guess we conclude our webinar today. Again, thank you for joining us today. And again, don't forget to download the free trial. You will really love it, use it. And if you have any question, you can always get a hold of me. We always say the program or the software will always deliver a higher quality product design with less time. Thank you very much. Have a great day. Thanks. Bye-bye.